Hello everyone, welcome to this class, DIT 1301 and DIT 1111, Operating Systems. I am Linda Sawe from the School of Computing and Informatics, Department of Information Technology. Welcome. Welcome to our lesson 1, whereby we will be looking at the overview of operating systems. And operating systems are basically very important to us in IT, and that's why we need to acquaint the learner with some of the terms that are critical in operating systems. And by the end of this lesson, the learner should be able to define the term OS. Operating system here is a term that every learner should learn, especially if you're in the field of IT. You need to understand what is an operating system. And then you also need to understand the different examples of operating systems that we have in the market. Then the learner should also understand the functions that the operating system offers. Then identify the different types of operating systems that we have. Then describe the history and generations of operating systems. And then last but not least is differentiate between the different operating system structures, how operating systems are laid out, how operating systems are structured. So we'll start by defining what an operating system is. And an operating system is an interface between a computer user and the computer hardware. Remember, computers don't talk. So we need a way of interfacing a user to the hardware. So the OS comes in between, or is an interface that comes between the user of the computer and the hardware, because you cannot speak to a computer. It cannot listen. It doesn't have the 5 senses like human beings. So you need a software that comes in between to interface or to be able to pass the commands that we are issuing to the hardware and the hardware responding to them. So an OS is a software which performs all the basic tasks like what? Like file management, memory management, process management, handling input and output, and controlling peripheral devices like disk drives and printers. So the computer offers us some capabilities like managing files. We have files in our computer system, files stored in the different directories of our computer system. We have memory. All computer systems have memory. So this memory has to be managed. We have processes. Every activity that is happening in the computer system is a process. We have to manage so that we don't have a crash in the process or even a conflict in the different processes that we are trying to run. We are using input devices. We are using output devices. So we need to plan how these input and output devices are managed. We need to control how the different peripheral devices are working. Maybe you're connecting a USB. How is that USB opened? How is that USB formatted, and so on? Maybe you have a printer. How do you install that printer? It is the operating system that provides us such services. Then some of the popular operating systems that we have are things like Linux, Windows operating systems, and Windows has so many operating systems. They keep producing operating systems on. Maybe after a few years, every year you get a Windows operating system. Here we have so many. We have Windows Vista, we have Windows XP, Windows 7, and so on. Then we have Microsoft DOS, the disk operating system. This was one of those Microsoft initial operating systems that were in the market. And then we have Android, the ones that we use for our smartphones, among others. So those are just but a few examples of operating systems that we have. Then still on the definition of operating systems is that an operating system is a program that acts as an interface between the user and the computer hardware and controls the execution of all kinds of programs. This is a diagram that represents that definition up there, where you see the operating system sitting between our computer system hardware part and the software part and the user. So that interface, that platform that provides a user with a way of communicating with the hardware, that is the CPU, the central processing unit of the computer, RAM, the input and the output devices that we have, peripheral devices, and so on, is what we are calling the operating system. Then what are some of the functions of the operating system? Now, the main functions of an operating system are we have main memory management, We'll explain what memory management is. Processor management, we'll also explain that. We have input and output device management. We have file management, security, control over system performance, job accounting, error detecting aids. We have coordination between other software and users. We'll explain each of those functions, starting with the first one, memory management. Now, our computer has memory that is used to hold the information as we process it. Therefore, managing of memory is very important, and it's the role of the operating system to manage our primary or main memory. This is the memory that the central processing unit writes to or read from when it's executing its tasks. So the main memory is a large array of words or bytes, where each word or byte has its own address, which we normally call the memory address. Now, an operating system does the following activities in regards to memory management. It keeps track of the primary memory. That is, what part of the memory is in use, by who, and what part of that memory is not in use. So it's the role of the OS to keep track of what memory is being used, what is using that memory, which process, and what part of memory is not in use. Then the next thing is that it also decides which process to get memory and when and how much. So each of the processes, as they are being executed, requires some memory for execution. So it's the job of the OS to allocate memory to different processes for how long and what amount of memory. Then it also allocates memory when a process requests it to do so. So as a process is running, it may request for some memory. It's the role of the operating system to allocate the different processes some form of memory as they request. And then again, it deallocates the memory when the processor no longer, or when the process no longer needs it or has terminated. So when the process is running, it's utilizing memory. But once it is ended, or once it has stopped happening or terminated, the memory needs to be deallocated. It needs to be freed. So it's the job of the job of the OS to do that. Then we have processor management. Now, in a multiprogramming environment, the OS decides which process gets the processor, when and for how much time. Now, most of the computer systems now are multiprogramming. They support several programs running at the same time. Therefore, many processes could be running or executing at the same time. Therefore, it is good to determine what process is given the processor. Remember, all the activities of the computer system are carried out in the central processing unit, the brain of the computer. Therefore, it's the job of the OS to determine which processor is getting access or is getting to utilize the processor, and for how long. It's very important. And then it's also the function of the OS to schedule the processes so that not one process hogs the CPU or uses the CPU for a long time. The processes need to keep running. So if you're running like 10 processes, it's the job of the OS to plan process 1 gets this amount of memory, then process 2 comes, gets this amount of CPU time until you have all the processes executed to a completion. So what then does the OS do in regard to process management? It keeps track of the processor and the status of a process. How far is a process executed, and is the processor free? Is the processor available? If the CPU time required to execute a process is, say, 15 microseconds, is this process executed like 1 microsecond? The next one is executed for another microsecond. This processor is now, or process is now executed for 14 microseconds are remaining. So you keep managing the processes until all of them are executed and to a completion in an easy way or in a manageable way. Then the next one is it allows the processor, that is the CPU, it allocates the processor to a process. So processes could be many, so it's upon it to decide what process accesses the CPU at a certain point in time. Then it deallocates the processor when a process is no longer required. So once a process is complete, it removes it or it deallocates it from the processor. The third function is device management. Then we say that an operating system manages device communication via their respective drivers. Every device has its own drivers. So it is the work of the OS to manage how this device communication is happening through the devices. And when I say device, I mean the input and output devices that we are using in the computer system. The keyboard, the mouse, the printer, the scanner, all those devices. And what does it do, or what does the OS do in regard to device management? It keeps track of all devices, what devices are installed in your computer system. Then it is also responsible for its tasks, that is I/O controller. It manages the input and output controller. Then it also decides which process gets what device and for how much time. If there are 3 processes trying to print, it schedules them so that it knows what process is printing currently, and then what will follow until you have all the documents or all the processes requesting for printing done. So it queues them, it puts them in a queue. Then it allocates the device in an efficient way, so that there is spooling and there is queuing and smooth running of the devices and the smooth access of the different devices that are there. Then it deallocates device. Once a task is complete or a process is complete, it frees that device and puts the device into ready mode, to mean it can now be in use by another processor. Then we have file management. Now, this is a very important feature also, and a file system is normally organized into directories for easy navigation and usage. So the computer system is organized in a file system, which organizes the different directories that we have. You may have directory C, directory D, depending on how you've partitioned your computer system. Now, these directories may contain files and other directories within them. So you can have a directory within another directory. So it is the job of the OS to carry out the following file management activities. One is it keeps track of information, location, uses, and status, among other things, of all the file system that you have. How many directories do we have? What folders are in those directories? It is the job of the OS to organize them, and it organizes them in a tree-like manner, so that a directory that is inside another directory will appear in a tree-like manner from that branch. Then we have, it decides who gets the resources. Again, it's a job of the OS to decide what file can be accessed, which processor can access which file. Then we have, it allocates resources, and last but not least, it deallocates the resources that are needed in the file manager. Then we have other functions. Other functions that are provided by the OS are, we have security. Things like passwords are supported in operating systems and other similar techniques that prevents unauthorized access to programs and data. So you can secure your files, you can secure your devices using passwords so that nobody can access them or unauthorized persons cannot access it. We have control over system performance. So it's the OS that schedules tasks. So it determines how the system will perform, so that you don't wait for a certain process to run for a very long period of time before you can do something else. Again, recording delays between requests for a service and response to this from the system. So it's the job of the OS to make sure that responses are prompt. Then it's job accounting. It keeps track of time and resources used by the various jobs and users. And then error detecting aids. Again, it produces some sound. Maybe it can produce a beep, an error message. You can get to know that there's a problem. Maybe you press a key for a long time, you will hear that beeping sound to alert you that there's a problem or there's a mistake. it is the job of the OS again to do that. And then another job that it gives us is coordinating between other software and users. So coordination and assignment of compilers, interpreters, assemblers, and other software to the various users of the computer system. So it can allow you, or it can coordinate that availability or availing of resources, software to different users in the system. Let's look at the different types of operating systems that we have. We have the most common types of operating systems are the batch operating systems. These are basically systems that do not interact with the computer directly. Batch systems accumulate whatever they are processing and then process it as a batch. That's why it's getting the name batch. And each user prepares his or her job on an offline device, for example, punch cards, and then submits to the computer operator. So the job is accumulated and then it's processed. That's why we call it a batch kind of system. Then the problems with a batch system is that it lacks interaction between the user and the job, and then the CPU is often idle because the speed of the mechanical input and output devices may be slower than the CPU. Since we are accumulating work and then processing, there's a lot of idle CPU time. And then there's difficulty to provide the desired priority. When you're scheduling jobs and have jobs that have a higher priority, it may be difficult scheduling them. Then we have time-sharing kind of operating systems. These are systems that enable many people located on various terminal devices to use a particular computer system at the same time. So you're able to share the CPU time, whereby you're given time to access, or the OS is given some time to access the CPU, and then another one is given an equal time until we are running concurrently. So there is limited idle time, basically, because the OS keeps switching from one process to another. Now, time sharing or multitasking is a logical extension of multiprogramming. So it allows several processes to run simultaneously but alternatingly. Then the next advantage of time-sharing kind of operating systems are it provides the advantage of quick response. Again, it avoids duplication of software and then reduced CPU idle time. The idle time for waiting is small. The disadvantages here is the problem of reliability. And then again, the question of security and integrity of user programs and data. So since a lot of data is being accessed at the same time, it can be risky. And then the problem of data communication. So sometimes the data communication may fail because we are trying to access many files at the same time since we are working with different processes. Then the third type is the distributed operating system. Distributed system basically use multiple central processing units to serve multiple real-time applications and multiple users. Now, data processing jobs are distributed among the processors accordingly. So this is for a system that has multiple processors embedded in them, and the processor communicates with one another through various communication lines like high-speed buses or telephone lines. Now, these are referred to as loosely coupled kind of systems or a distributed system, whereby we have several processors supported in that computer system, and the OS will allow to be able to work within that distributed kind of environment. Now, the advantages of a distributed system is that that resource sharing facility makes it, or is able to use the resources from another or from at another point where it's available. So you're able to access a resource that may not be necessarily available here, but it's available in another environment. And then exchange of data is very fast. And then if one site fails in a distributed kind of environment, then you can access another part, or the remaining site may potentially be working or in operation. And then we have better service to customers. So customers can easily be served, and then reduced overload, or basically reduction of the load on the host computer. Since it's distributed, there is no computer that is overloaded, and then we have a reduced delay in data processing. The next type of operating system is the network operating system, and the network operating system runs on a server, and it provides the server capability to manage data, users, groups, security, applications, and other networking functions. So a network operating system basically provides server capabilities that is able to manage different users, manage different types of groups, security, applications, and such like things. And then the primary purpose of a network operating system is to allow sharing of files and maybe peripheral device access like printers. And it allows multiple computers in a network to typically share some resources or even communicate with each other. And then examples of network operating systems are operating systems like Microsoft Windows Server 2003. We have the Microsoft Windows Server 2008. We have UNIX, Linux, MacOS X, and then we have Novell. We have and BSD. All those are some of the common examples of network operating systems that provide us with those server capabilities. Then what are some of the advantages of network operating systems? We have the centralized servers are highly stable. Then security is server managed. And then we have upgrades to new technologies, and hardware can easily be integrated into the system. Then we have remote access to servers is possible from different locations and types of systems. So these are basically server capabilities that network operating systems provide for us. Things like security, centralized kind of management is very stable because you are sure that your network is centrally managed. And then remote accessing to servers is possible, meaning you can access the server from wherever, despite your location. Then what are some of the disadvantages? High cost of buying and running a server. It's very expensive maintaining and running a server, so that may be an issue. Then dependency on a central location is very shaky, because once the central device is having a problem, it means the entire network is down, or the entire operating environment is down. So it is good to note that when you have a central location, it might be very risky, because once that central device is having a problem, the entire network is down. Then we have the regular maintenance and updates are required. You need to keep your server up to date, or your network operating system up to date. Then the next type of operating system is the real-time operating system. Now, this is a system that requires time interval to process and to respond to inputs. So that it requires a very small interval whereby you give it an input and an output is expected immediately. So you see the term real time, meaning it is at that particular time when it's happening. So the input is expected within a very small time interval. And real-time systems are used when there is a rigid time requirement, whereby you need to have a live kind of streaming for a thing, whereby time is very critical here. Maybe time can mean maybe a modification is being done or something, especially for things like elections and such like things. You may require a real-time kind of operating system whereby whatever is being done is streamed on a live basis, whereby something is being relayed like exactly the same time where it's happening. And real-time systems have a very fast flow of data, and real-time systems can be used as a control device in a dedicated kind of application. In an application where maybe time is a major factor or is a critical factor, you can use a real-time kind of operating system. And then there are two types of real-time operating systems. We have the soft and the hard real-time operating systems. Hard real-time operating systems guarantee that critical tasks complete on time. So time is very critical in a hard real-time system. And in a real-time system, secondary storage is limited or missing, and the data is stored in the read-only memory. So they write hard real-time systems write and read from the read-only memory. Now, in these systems, virtual memory is almost never found, so you don't require really the virtual memory. But for soft real-time systems, they are less restrictive, so that time is not really critical, and a critical real-time task gets priority over other tasks and retains the priority until it completes. So for a task that is critically real-time, it will get priority over the soft real-time systems. Then the soft real-time systems have limited utility compared to hard real-time systems. Then what are some of the operating system services? Now, an operating system provides services to both the users and the programs. So an OS plays a key role to users, who are the people who are using the computer, and again to the programs that are running in the computer system. It provides programs with an environment to execute, so it provides it with that platform to run, and then it provides users the services to execute the programs in a convenient way. So for us users, it provides us with a platform. It provides us with services that we need in order to execute the programs in a convenient way. Now, what are some of the operating system services that the OS offers us? One is program execution. 2 is input and output operations. 3 is file system manipulation, communication, error detection, resource allocation, and protection. Then there are other system properties or other operating system properties that we need to learn. We've talked of batch processing, whereby it's a technique that the operating system collects several programs and data together before it is processed. So for batch, when you hear the word batch processing in regard to OS, it refers to that operating system or that concept of collecting programs and data first, accumulating it before it is executed or processed. Then multitasking is whereby multiple jobs are executed by the CPU simultaneously by switching between them. So when you hear of the word multitasking in regard to operating system, is whereby we have several tasks run at the same time, but we switch between these tasks or jobs. Then we have multiprogramming, which is sharing the processor when 2 or more programs reside in memory at the same time. This is whereby you could be running several programs at the same time, and they are both in memory. When I say both in memory here, I mean the primary memory. So multiprogramming basically supports several programs running at the same time, and they are in memory. Another term is interactivity. Interactivity here refers to the ability of users to interact with a computer system. Now, the OS provides us with interactivity, things like the command line interface, graphical user interface. It provides us with some form of interactivity whereby you kind of communicate with the OS in a way so that you're able to pass instructions that you require. We've talked of real-time systems. Real-time systems here are dedicated, embedded systems that typically read from and react to sensor data within a fixed period of time. We've talked about real-time type of operating systems where we've said that time is critical here, where you give it an input and expect an output immediately within a fixed period of time. Then we have distributed environment, which refers to multiple independent CPUs or processors in a computer system. So here we have independent computer systems that are grouped together and operating like it's a family of computers here in a distributed kind of system. Then we have another term, spooling. Spooling is similar or simultaneous to peripheral operations online. And spooling refers to putting data on various input-output jobs in a buffer, whereby you are able to switch between tasks or carry out tasks within another small form of memory we are calling a buffer. Now, this buffer is a special area in memory or hard disk which is accessible to input and output devices like a printer. A printer can be spooling between jobs or spooling between different jobs that it's carrying out. So that's what we are referring to as spooling. It's that simultaneous peripheral operations online whereby you could be switching between tasks, and these tasks are stored in a small memory area which we are calling a buffer. Then we look at the history of operating systems, and operating systems have evolved through several phases. It starts with the 1940, whereby we have our early computers that did not have any operating systems. These computers were very analog and very basic. They didn't have any operating systems in them. Then in the 50s, we had the operating systems that could execute one job at a time. Those are single tasking kind of operating systems, and it included technologies to smooth job-to-job transition. So they were just having very basic kind of transitioning mechanisms where you finish one job, move to the next job. Then it had a single stream batch processing system whereby it accumulated tasks, then executed it. Then we have programs and data submitted consecutively on a tape. Now, the computers of this time used the punch cards and the paper tapes for input and output. So that processing was submitted consecutively on a tape. Then in the 60s, we have this. We still have the batch processing systems, when then we could process multiple jobs now at the same time. So we could have things like multitasking and multiprogramming being introduced. And like the previous in the 50s where we had single tasking. Then when we have one job could use a processor while other jobs used peripheral devices. So you could be using the processor to carry out a task and accessing a peripheral device like a printer maybe. And then we have advanced operating systems developed to service multiple interactive users. Then in the 60s, we still had time-sharing kind of systems, whereby we had developed support for many simultaneous interactive users, and then turnaround time was reduced to minutes or seconds. So changing from one task to another became shorter, and this is the time between submission of a job and return of its results. So when you give an input, how long was it taking to get an output? Then we had real-time systems here, whereby response time was really short, or a short period of response time. Then we had improved development time and methods. Then we had address more memory locations than actually exist. That is use of virtual memory. So you could get that the memory or the read-only memory that we had could now be more than what is available. That is, creation of the virtual memory came into existence. And then in the 70s, this is where we had the multimode time-sharing kind of systems, whereby it supported batch processing, time-sharing, and real-time applications. And then we had personal computing only in incipient stages, and then we had fostered by early development in microprocessor technology. If you remember well, in the history of computers in the 1970s, that's when we had the microprocessor technology coming on board. And then we had the TCP/IP protocol was developed, and standard communication protocols came into existence. And then we had this was widely used in the 70s. The computer systems were widely used now in military and even in a university setting. Security problems came into existence, and then growing volumes of information passed over vulnerable communication lines. So we would have some challenges in communication and passing or sharing of information. Then in the 80s, this is a decade of personal computers and workstations. We now had computers like the desktop computers coming into existence, the laptop computers and such like things. And then we had distributed computing coming into existence, whereby we could work remotely from different locations. And then personal computers proved relatively easy to learn and to use, since we had graphical user interface coming into existence. And then transferring of information between computers via network became more economical and practical. Now networks started being set up, and sending of information via this network became easier. Then let's look at the different generations of operating systems that we've looked at in our history of operating systems. And the first generation of operating systems is looked at to span through 1945 to 1955. Now, this is the only operating system. This is where the only operating system was a person. All machines were operated hands-on. They were manual kind of machines, whereby if you want to pass an instruction, you either keyed in the instruction as it is using a basic language here, or basic computer language that you had to communicate to it, or even use keys or buttons where you press whether you want to pass something on or off and such like things. So here we didn't have any operating system at all. Then we moved to the second generation, whereby we had the batch operating kind of system, and where tasks are accumulated before they can be executed, and then a computer operator takes care of the system administration, and the operator collects a batch. That's why we get the batch operating system of programs from several programmers, feeds the programs into the computer, and then that is the programs are now executed and the results sent back to the programmer. Now, today, batch operations are performed automatically. Back then, you had to manually do it, and then compute jobs line up in a FIFO, first in, first out job queue. That is first in, first out. Whatever job comes first is what will be executed first. Then the third generation is where we had multiprogramming, where we could switch between different programs in memory, that is random access memory, as shown below. We have job 1, job 2, job 3. Job 1 is waiting for input, job 2 is running, and job 3 is ready to be executed. So that is multiprogramming, whereby we have several programs residing in RAM at the same time, and they are all concurrently being executed. Then we also have what multiprogramming enables. It enables time sharing, whereby we are switching between jobs, dividing the CPU time in slices of equal amounts, and we are giving each of the jobs some time to execute until we finish. Now, the slices are divided fairly among competing jobs. In this case, competing jobs are the jobs that we have in our processor that are ready to be executed. Then it also allows interactive processing, whereby the user does not have to wait for one process to be finished until the next process can be started. So they are run like interactively, whereby you allow a process to execute, give a chance to another process to execute for a certain period of time until we have all the processes executing partly, and then give a chance another round until you finish all the processes or all the execution. Then we move to the fourth generation, where we have multi-user kind of operating systems. When you say multi-user, it supports many different users to share the computer system at the same time through time sharing and multiprogramming. So you can allow them to share the CPU time, these different users that are carrying out different operations at the same time, and allow multiprogramming. Several programs residing in the random access memory together at the same time, and they are being executed. A good example of such a multi-user operating system is UNIX, MacOS X, and Windows NT. Then the OS divides its system time into time slices, milliseconds, small time slices, and each of the time slices is now allocated to the different programs or the different users at the same time. Now, this gives each user the illusion to have his or her own machine. So it kind of creates a virtual machine whereby each of the users is assigned some resource they are able to use, and they are appearing like they are on their own machine, yet it's a virtual machine. Now, the efficiency of time-sharing systems depend on, of course, the speed of the processor. The speed of the processor is really critical. Then the length of the time slices, how much time does each of the process require? Then we have how many users perform operations that require a full time slice. So again, how much time do we need, and how much do we need, or how much of this time should run the process completely. Then a multi-user OS is mainly used in distributed rather than centralized environments where several machines share resources over a network. So again, multi-user are mainly used in that kind of environment where it's distributed rather than a centralized place. So it can't work very well for a centralized kind of system. It's good for a distributed kind of environment. Then what then do single-user OS and multiprogramming OS give us? It gives us cooperative multitasking, whereby we can switch between programs in only if those programs explicitly cooperate. So there are some programs that may conflict. There are some programs that may try to access the same data at the same time. That may mean that they are not explicitly cooperating. So single user and multiprogramming can work well in the case whereby all the programs that are participating are explicitly cooperating. Then where we have preemptive multitasking, whereby you can interrupt each of the programs that are running to give time slice to the different programs that you want to run. Then it lets the OS to switch between tasks at its own discretion. That is what we mean by preemptive multitasking, whereby that voluntary preempting between the different programs can happen, and then it performs different tasks at the same time. That is, you can print, you can compile, you can search a file on the web at the same time. Another advantage that NOS provides us is file sharing. That is allowing users to share files easily and to send files, or even maybe interactively access similar files at the same time. It also provides communication scheme, whereby you're able to communicate online or to communicate via a network, and then it runs independently from other computers on the network. So it is able to run independently of other computers in that particular network. What are some of the operating system structures that we have? The aim of basically an operating system structure is to engineer carefully so as to function properly and to be modified easily. So the way the operating system is laid out or structured is very key to ensure that it is functioning properly and it can easily be modified. So operating systems are broadly classified into 3 categories based on their structuring mechanisms. Here we have 4 listed, though we've said there are 3 main, but we have 4. We have simple structure, whereby it's just a simple kind of structure. We have the monolithic operating system structure. We have the layered operating system structure, and then we have the virtualized operating system structure. We'll discuss each of the structures, starting from the simple structure. And the simple structure is whereby the operating system, like DOS and original UNIX, did not have any well-defined structures. These are the early operating systems, the Microsoft DOS, disk operating system, and UNIX. They are simple operating systems that didn't have any structure at all, and there were no CPU execution modes like the user and the kernel here, but the errors in applications could cause the whole system to crash. So since there are no layers, there are no structures, there are no different hierarchies established, when the OS crashes, it means that the system is crashed, or the entire system is crashed. So it just simply puts all the different items or services that are provided in the operating system in that area, whereby we don't have any structure, we don't have any layer or any hierarchy. Then we move to the second type of structure, which is the monolithic operating system. Here, the components in the monolithic operating system are organized randomly, and any module can call other module without any arrangement. So they are organized in a way that is random. There is no structure really that they follow. They are random, and any module can access or call another module. When I say call here, I mean request or send a message or receive a message from another module. Now, applications are separated from the operating system itself. When I say applications here, I mean software applications, and that is the OS code runs in a privileged processor mode. So you know the operating system is a program, so it has its own code. It runs in a privileged processor mode, that is the kernel mode, with access to system data, so it can access what data is in your system, and the hardware. It can access any hardware with that mode of privilege. And then applications run in a non-privileged processor mode, that is the user mode. So it distinguishes two modes here. We have the kernel mode, which is the privileged processor mode where the OS resides, and then we have the non-privileged processor mode where the user or where the applications reside, and this is where the user accesses, and it is limited to the user. Then we have a diagram. It's limited to the interfaces available and to the system data access. So we have those two things. The operating system will reside in that kernel mode. The application programs will reside in the user mode. So that gives us a clear distinction here, and all of them ride on or run on the hardware. Then we have the layered mode here, or the layered operating system structure. This is where the components are organized into modules and layers, and from one on top of the other. So we have the layers are created in a layered mode, as the name suggests. And here the operating system layer is an implementation of an abstract object made up of data and the operations that can manipulate the data. Then each module provides a set of functions that other modules can call. Then here we say the interface functions at any particular level and can invoke services from provided from the lower layers, but not the other way around. So the layer that is at the top can access the lower layers, but not the other way around. The layers at the bottom cannot access the layer above it. Now, the bottom layer, say layer 0, is the hardware, and the highest layer, say layer N, is the user interface. Then we say that a typical operating system layer, say layer M, consisting of data structures and a set of routines that can be invoked by a higher level layer. So if a layer is on top of another layer, it can access the information that is below it, but not the one above it. Then layer M in turn can invoke operations on the lower level layers. So it is clear. If you have M or layer O, layer O or layer O on the layer 0 on the bottom and layer N at the top, the layer that is above you, you cannot access that service, but you can access the one that is on the or the layers below the particular layer that we are at. We have an example given to us here where we have the kernel mode with the different applications, with the different OS structures here, and the user mode with the application programs that we have. So the operating system is here, and these are the application programs that we have. Then here we have the kernel and the different operating system functions that we have. We have things like signal, terminal handling, character input output system, and then we have terminal drivers, we have file system swapping. All these are organized in different layers, and as we've said that whatever is on the lower layer can be accessed by the ones that are on the upper layer, but not the other way around. So that is basically the layered kind of operating system structure, whereby the different modules or the different operating system functions are organized in modules, and each of the modules in a layer. And as we've said again, these layers are put in different levels, and one module can access what is below it, but not what is above it. So that is something to learn about the layered kind of OS structure. And the last OS structure is the virtualized kind of operating system. And the fundamental idea behind the virtual machine is to abstract the hardware of a single computer, that is the CPU, memory, disk drives, network interface cards, among other things, into several different execution environments, thereby creating the illusion that each separate execution environment is running on its own private computer. So this is just basically creating a virtual kind of machine, whereby we have different components of the computer existing like an actual machine that is running independently or on a private computer. Now, by using the CPU scheduling and virtual memory techniques, an operating system can create the illusion that a process has its own processor with its own virtual memory. Now, each process is provided with a virtual copy of the underlying computer, an interface that is identical to the underlying bare hardware. So it's just basically a way of creating virtual machines that can allow a process to run individually on a virtual machine like it's actually running on an actual computer. Then it enables sharing of the same hardware, yet run several different execution environments. That is an operating or a different operating system concurrently. So it is just the concept of creating virtual machines and virtual operating systems within a computer system for purposes of allowing that quick processing of tasks and carrying out tasks. Now, this is where most of the operating systems are now. They create those virtual machines that have equal resources that are available. The processor, the CPU, the memory, all these are virtualized to look like the processes are being executed. So again, the concept of virtual machines is very good and well embraced, though you need a computer that should be able to support this kind of virtual machines and virtual kind of devices that you are able to run different processes within the different machines at the same time. So that is the end of our introductory class for operating systems. Thank you for your attention.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.